Hi students, welcome back to geology. So now that we know that continents do move, what on earth could move a continent? We know that rocks don't exactly have wheels, so how does this work? So your pondering question as you read through the slides and then you listen to the video is how might heat from deep inside the earth cause materials to move? So think about how hot air rises and cool air sinks. And hopefully by the end of this, that will make sense. So let's first talk about the layers of the earth. So the earth has three basic layers. We have the crust, which you stand on, the mantle below the crust, and then the core, which is the interior. Okay, and then the core is developed or separated as the inner core and outer core. Okay, so we have the crust, which is the outermost layer. It's the thinnest layer, ranging from about 5 to 70 kilometers in thickness. And then the mantle is just below that. It is the layer that is the thickest, and it is about 2,900 kilometers thick, which is crazy. And then we have the core, which, like I said, is divided into the outer and the inner core. The outer core is liquid and the inner core is solid. And those interactions there create our magnetic field because they're made up of iron and nickel. So looking at the Earth's crust more in depth, again, this ranges from 5 to 70 kilometers in thickness, and that depends on whether we're looking at continental crust or oceanic crust. Continental crust is much thicker, which is why it stands above the ocean water level. And so this is usually about 35 kilometers thick on average, but it can be thicker, especially when you're looking at really tall mountain ranges like the Himalaya. And then we have the oceanic crust, which is a much thinner layer. And that layer is somewhere around 7 kilometers thick, and it makes up the ocean basins, which is why the water sits on the oceanic crust. Okay, the other big difference between these two is that they are made up of different things. So the continental crust is a thick crust, like I said. It's buoyant, it's less dense than the oceanic crust, and that comes from the type of rock that it's made of. So most of the continental crust is made up of granite, and it's mostly old material. So this makes it much less dense than what the oceanic crust is made up of, which is basalt. It is very dense, and so it'll sink under continental crust when these two crusts are colliding against each other. Okay, and we'll talk about that in the future lectures. But for now, things that you want to remember is that continental crust is much less dense than oceanic crust, and that oceanic crust is very young in comparison to continental crust. All right, so moving down into the mantle, we do separate the mantle into upper and lower. And the mantle is a layer that's below the Earth's crust. And again, this is the thickest layer at 2,900 kilometers on average thickness. And the upper mantle is relatively rigid and contains what we call the asthenosphere, which is a semi-fluid layer that allows for the movement of tectonic plates. And we'll get into that. We'll revisit that in a next lecture. And then the lower mantle is what contributes to the overall convection and heat transfer within the Earth's interior. And so this is where we're going to start getting into how do the continental drift theory even work, right? So what is the mechanism behind it? So if I told you that Earth was a giant lava lamp, well, the mantle is a giant lava lamp. It sounds kind of silly, right? But it's not exactly wrong either. So one of the things that's happening inside the crust is a heat transfer. And so we know there's 3 types of heat transfer. There's radiation, which is like heat that you feel from the sun. There's conduction, which is you touch something that's hot and then your hand gets hot. And then there's convection, which is what's happening in the mantle. It's what's happening in a lava lamp. So with a lava lamp, there's a heating element at the bottom, which heats up the material. When the material gets warm, it becomes less dense. And when it becomes less dense, it rises. This also happens in air as well. Warm air rises, right? You've probably heard that many times. And it rises because it becomes less dense from the heat. Okay, so as it goes to the top here in the lava lamp, it starts to cool down a little bit. And so that material will become more dense again and fall. And so you get this cyclical pattern in the lava lamp of rising and falling. And that also happens in a boiling pot of water. So when the water is really close to the heat source or the stovetop, it heats up, becomes less dense, comes to the top, gets cooled down again a little bit, and then falls from becoming more dense. And that creates your bubbles in your boiling pot of water. So this is happening inside of the earth, inside the mantle, and we call this mantle convection. And it describes the movement of material within the mantle, and then it also helps us describe how things are moving on the Earth's crust. Okay, so in 1928, Arthur Holmes figured out that this is what was happening in the mantle. And if you look at these convective cells, they can pull away from each other at the crust, or they can come together at the crust, just depending on how material is moving in the mantle. And that will help drive moving continents in different directions or moving the crust around. Okay, so mantle material that is close to the core heats up, becomes less dense, rises towards the crust. As it rises towards the crust, it starts to cool down, becomes more dense again, and falls. And so you just get this cyclical pattern within the mantle of heat. So here's a really cool graphic showing you what that kind of looks like. You can see material coming from the core rising as it's warmed up and becomes less dense. And then as it cools down towards the crust, it starts to cycle back down closer to the interior of the earth or the core before it comes back up again. So when we start diving into the Earth's core, again, we have the outer core and the inner core. The outer core is our liquid layer, and it's mainly molten iron and nickel. It has a thickness of about 2,300 kilometers. And then our inner core is a little bit smaller than our outer core, and it's solid. And the reason that it's solid is because there's no possible way, there's too much pressure at that depth for anything to move. And so the inner core becomes solid, and the iron and nickel that comprises that inner core cannot move. And so the interaction between the inner core and the outer core being solid and then versus liquid, that creates a magnetism that creates the magnetic field around Earth, which protects us from things like solar winds and solar flares and things like that. So some final thoughts for your notes is explain in one sentence how the asthenosphere enables plate motion. So think about that. I'll see you in the next video. Bye.